Imagine you just built a brand new social media app. It's working perfectly, but then it goes viral, and suddenly 10 million users are trying to log in, post, and comment all at the exact same time. Like most early apps, your data is probably sitting on a single server, using a traditional relational database. This means every piece of user data is being forced into a very strict, rigid grid of rows and columns. When that grid gets overwhelmed, developers usually try an intuitive fix called vertical scaling. In plain English, that means buying the absolute biggest, fastest, most expensive supercomputer money can buy to handle the load. There's a hard physical limit to this approach. A petabyte is 1,000,000 gigabytes, and you simply can't cram that much active data into one computer's memory, no matter how much you spend on the hardware. This is the problem companies like Facebook had to solve. They have billions of active users, yet their systems don't just melt down when the world logs in. Supporting that many people at once requires moving past the idea of one almighty machine. It requires a swarm of thousands of ordinary ones working in sync. This strategy is called horizontal scaling. Instead of building one giant skyscraper, you buy 1,000 standard working-class computers and link them together. But to make 1,000 computers share the work, we have a formatting problem. Those traditional, rigid spreadsheet databases we talked about earlier, they are incredibly difficult to chop up and split across hundreds of different machines. The solution is a NoSQL document database. It's a way of storing data that looks less like a spreadsheet and more like a collection of flexible, self-contained file folders. These folders are independent. One user's folder might hold 5 photos, while another's holds 5,000. Because they aren't tied to a strict grid, the system can pick up any folder and move it to any computer. Ditching their rigid rows and columns makes the data portable enough to scatter across a massive network. Now that our data is highly portable, we need a way to organize those folders across 1,000 different computers. The technique used to do this is called sharding. Think of sharding like a highly organized mailroom. The system uses a specific key to automatically route data. For example, it sends users A through C to server 1 and D through F to server 2. Relying on 1,000 standard computers does introduce a guaranteed headache. Hardware eventually fails. Hard drives break, power goes out, or machines simply catch fire. To protect your photos and posts, the network uses replica sets. Every piece of data is instantly copied to several backup computers. If the main server goes offline, a backup takes over without missing a single folder. By expecting parts to break and building automated replacements, major apps can survive physical hardware crashes without ever showing you an error screen. But having your data spread across 1,000 machines creates one final hurdle. How do you find one specific piece of information when it's buried in a petabyte of scattered folders? If a single computer tried to search through every folder on every server, one by one, a simple search query could take years to finish. To solve this, developers use a parallel processing engine called MapReduce. It works by dividing the labor. First is the map phase. The system asks all 1,000 servers to check their own local data at the exact same time. Then comes the reduce phase. The network catches those 1,000 small answers, groups them together, and condenses them into a single final result in milliseconds. At this level, search speed comes from thousands of servers scanning their own small patch of the network at the exact same moment. Designing systems for this much data is an exercise in coordination. It's about managing thousands of small parts rather than relying on one powerful one. It requires 3 pillars working in harmony: flexible data packets, distributed storage grids, and parallel searching. So when you sit down on a Friday night and load up a massive global streaming catalog like Netflix, the menu on your screen appears in a heartbeat because of a massive mechanical choreography happening across thousands of blinking server lights. The most massive digital systems in the world aren't magic. They are just thousands of ordinary parts working together perfectly.